continent. Here's my ocean coming along, and the ocean's going down under the continent. Every once in a while, a little piece of that old ocean floor wouldn't subduct. It would get caught on the edge of the continent and just get plastered on there and stick there. And one after another, that happened. And our whole west coast, most of California, Oregon, Washington, inside passage up to British Columbia, the southern part of Alaska, are all just bits and pieces of what we call accreted terrains. Remember the process of accretion making the solar system, where things were sticking together? Same thing here. These bits and pieces of ocean floor that wouldn't subduct all got stuck on the edge of the continent. It makes geology just incredibly difficult there. You're walking along, you think you've got it all figured out, you take a step and you're in a new ocean floor bit. And it's all different. It's really crazy stuff. So we also call these suspect terrains, because they are just, you always suspect something's going on. So we see that these aren't old volcanoes, these aren't unexplainable things. They make sense. They're just part of the subduction zone of this plate tectonics concept. So if we look at it, we see that they're really somewhere between, depending on how you count them, how big you consider a major plate to be, somewhere between a dozen to about 18 big tectonic plates. And they're all separated by things going on at the plate edges. For instance, here, we're making new crust. This is a big spreading ridge. So plates are moving away from each other. We're making new crust there. These are what we call divergent boundaries, because they're diverging from each other. Or here you can see we've got subduction going on. The plates are coming together one way or another. One plate is going down, the other plate's riding over the top of it. These are the big recycling centers. We call these a type of convergent boundary because they're coming together, convergent. And here, where we see basically India colliding into Eurasia, we're making the Himalayas, see it better over here, again a convergent type of boundary, but now it's a continental mass slamming into another continental mass. Neither of those masses wants to subduct. That lighter granite stuff wants to stay on top. So now, instead of a subduction zone, it's like a front-end car crash. It just comes together and stacks up. That's why the Himalayas are where they are. And in other places, we just have plates sliding past each other. For instance, this plate's moving that way. This plate right in here is moving the opposite direction. So we just have these zones where they're not coming together, they're not moving apart, they're sliding next to each other. And those are what we call transforms. Okay, so let me ask you this about tectonic plates. They always move at the same rate, they're always moving away from each other, they always move in various directions at various rates, or they subduct at divergent plate boundaries. There's only one correct answer here. People like C. Well, we know that they don't subduct at divergent boundaries. Divergent boundaries are where they're coming apart, and that's where we're making new crust, not recycling old crust. Always move away from each other? No, we know they move in a bunch of different ways. They move apart, they move together, and then move next to each other sideways. That's not right. Do they move at the same rate, or do they move in various directions at various rates? If we go back and we look at our plate, lithosphere plate picture, notice with these arrows that it shows that they're moving in numerous directions. And if you think in terms of this being a sphere, it's impossible for them to be moving all at the same rate. To be opening at the large diameter of the sphere at the equator, it's got to be moving a lot faster than it would be up at the small diameter by the poles. So things have to be moving at different rates. And look at this plate here. Here's the North American plate. Here it's moving apart. Here it's moving together. On the other side, here it's sliding past. I mean, we can have all sorts of different motions and different velocities of these motions all at the same plate. It's going to change along the margin of the plate depending on how it's interacting with the plate next to it there. So the correct answer here for our question is going to be C. Various directions, various rates. So if you think about it, when we talked about plate tectonics, we've really only got three big things that we have to worry about. What's happening where plates are moving apart as divergent boundaries, making new crust. What's happening where we're crunching things together, using up the crust to make space for the new crust. And what's happening as plates just slide past each other. We're going to see very different styles of Earth on the surface as these events occur. So let's kind of take a look at, first of all, at the divergent type of boundaries where plates are moving apart from each other. It doesn't have to start out in the ocean. In fact, oftentimes it starts by a continent rifting or breaking apart, just like Pangea started. But it oftentimes ends as an ocean. For instance, here I've got a landmass, continental crust. I start with this hot plume coming up underneath it, and what's going to happen to that crust? It's going to heat up. It's going to start to expand. And as it does that, it's going to form an arch, because the easiest way for that to expand is to simply go up. Least resistance, right? But that also means that I'm stretching the crust. Instead of just going straight across, now it's got to go up and back down. So that crust is going to start to fracture. It's going to break apart. It's going to thin out a little bit. And I'm going to start to see these blocks now break up, and eventually the top block, the keystone of the whole thing, is going to drop down. I'm basically pulling this apart. Remember, I'm starting this plate motion of moving them apart, diverging. So I'm making space now for these blocks to simply fall down into the hole. So that's what I say. I create this rift valley. I'm going to have hot materials making their way to the surface. I'm going to see lava escaping on the surface, making igneous rocks. I'm going to be weathering and eroding these new cliffs, and those sands and gravels are going to be carried down into the valley. So I'm going to see a real mishmash of rock down there. Some of it's going to be melted igneous rock. Some of it's going to be sedimentary sands, gravels, clays, real mishmash of stuff. And as the process continues, eventually it's going to widen out, and it's going to become a long linear sea. It's going to just keep forming this valley, and eventually, bingo, it tags into an ocean someplace, and that ocean comes in and floods that valley. So now I've got a long linear sea. And as the process continues, that sea keeps opening up, and over millions of years, it gets wide enough where it's not linear anymore. It's now a big, broad ocean, like the Atlantic. Okay. See, even Syria agrees. So, if I look at it, and I look at these different stages, I can kind of see this happen. In East Africa, right down through here, I see these early stages where the continent is rifting. I start to see the beginnings of a rift zone, and what I see is the East Africa Rift. And you can just follow this rift right down through here. You just follow it right along. one little volcano after another along this rift. Now you'll notice I've got this rift here, I've got an open rift here that's a further stage, and I've got a rift running up here through the Red Sea, an even further stage. So why did these stages get further along and this one is kind of lagging behind? And why are they oriented this way? Well, this is what's known as a triple juncture, right here at the far triangle. Notice how these arms all come together right here. And if you were to measure the angles between these arms, they'd each be roughly 120 degrees. All the same. Have you ever popped a balloon with a pin? And it goes pop, right? But slow it down. Do it in slow motion. And as the pin goes through the film of the balloon, what you see is not a pop, but you see from that pinpoint, you start to see the skin of the balloon start to rip. It starts to tear open. And it tears open in this pattern, in this triple juncture pattern. One rip up, one there, 120 degrees between them. That is the most efficient way for the energy to affect that failure. Same thing happens here. Just like popping a balloon. Now, not every arm is going to go at the same rate. And once one kind of takes off and relieves the stress, the others don't need to work quite so hard. So what you usually see is one will open up faster than another one, and one will essentially kind of fail. And that's what we're seeing here. It's all the same system. This arm here through the East Africa area is the failed arm of this triple juncture, or this rift. Okay, let's kind of look at the arm that we're looking at here. Here is the Gulf of Aden, and here's the Red Sea. And what I've simply seen there is, instead of being stuck up here like I am with the East Africa rift, I'm kind of in here with the rift. Some of the rift is like this, some of it's like this. But here is a long linear sea. Do you see a long linear sea here? The Red Sea is this stage. This area right here, well, we certainly haven't gotten there yet, but given enough time. If I look at it, here's the Red Sea. And I'm standing right here in the Red Sea, looking up along right in here, looking north. And here's the end of the north of the Red Sea. Look at these downdrop blocks. Notice how they're opposite on each side. Here's the Keystone area. So I'm looking at this kind of a system that's been flooded here up to this point right there. Isn't that a beautiful example of what's going on there? You can just see it in cross section. The Gulf of Aden has just gotten a little further along the process. Okay, so true or false? The Mid-Atlantic Ridge is an example of a divergent plate boundary. Everybody is going to get this one right, so I'm only going to give you 10 seconds. Okay. See how we did? Almost. I think two people said, oh, he thinks we're all going to get it right. Well, we'll show you. Okay. Yeah, it's just the next stage in this whole process, isn't it? We have basically just taken that long linear sea, the Red Sea, and we've just continued to open it up, give it enough time, a few million years, and we got the Atlantic Ocean. So, if you were going to ask me, well, what's the world going to eventually look like here? I would say the Red Sea is going to be the new Atlantic. That would be one of the choices. Okay, let's change change gears, and instead of looking at divergent plate boundaries, let's look at convergent plate boundaries, where plates are coming together, where we're recycling the old crust. Now, I'm talking about essentially the ring of fire. Remember, volcanoes and earthquakes kind of go hand in hand. So you can just see how the Pacific, being ringed by earthquakes, is also ringed by volcanoes, therefore the ring of fire name that it gets. And it's nothing but subduction zones. All the edges of the Pacific are subducting. So that should tell you, if you were asking me what's the new world going to look like, I'd say the Pacific is going to be a lot smaller. It's getting eaten up all around its edges. It's subducting. And we see it happening in some different ways. Along Japan, here are the islands of Japan. Here's the trench where the Pacific plate is being subducted underneath. As that plate melts, that material makes it back to the surface, and Japan is nothing more than a series of volcanic islands, all being made from the subducting plate that's going down underneath it. That's why Japan is just riddled with earthquakes and volcanoes. Horrible place to have any stability. And notice in this case, I've got a Pacific Ocean plate going under another ocean plate. So the islands that make up Japan are being built as volcanoes right off of the sea floor, which is the overriding ocean plate. So the volcanoes have to build up to sea level and continue building to become islands to make Japan. And you'll notice that all these islands now form right along and parallel to the island, or the trench. And notice that the trench and the islands are curved. They don't run straight, but they curve. And part of that's simply because we're dealing with the curvature of Earth. So we call this an island arc system. Islands because they're building off the seafloor, forming islands. Arc because of this curvature of the trench and the parallel island system that goes with it. So that's an island arc system. Ocean-ocean collision. On the other hand, if I were to go look at what's going on, say, in Washington and Oregon, there I've got collision between two plates. The oceanic plate, the Pacific plate, is subducting, and it's going under the continental United States, under North America. The granitic plate is lighter. It doesn't want to subduct. The oceanic basalts are denser. It's more than happy to subduct. So it's a pretty clear-cut case. The denser plate here is going to subduct. Down goes the ocean plate. Here's my ocean trench. But notice how this continental edge is kind of scooping up, scraping up some of the sediment that's on top of the plate. And it's kind of filling the trench in a little bit, kind of bulldozing sediment along. And there's plenty of sediment there because that's where it's the thickest, and that's where it's the closest to the source of the continent. So all that fits our picture of what's happening to the thickness of the sedimentary cover. And as that plate, that ocean plate subducts, just like under Japan, it hits a depth, it melts. That melt now is hot. It rises, it finds its way back to the surface. But now, instead of coming up on an overriding oceanic plate, it's coming up on top of an overriding granitic continental plate. So I'm not getting an island system built from the seafloor up. I've got a series of volcanoes that are being built on land on top of the granitic plate, on top of the continent. They parallel the trench. They tend to curve a little bit, just like here. But there they are. In the case of Oregon and Washington, it's the Cascade Range. And Mount St. Helens, everything through there. Rainier, Baker, you name it. All of those are currently active volcanoes, all part of the subduction system. So when I've got this continent overriding this basalt, it's pretty much always going to be